So that's blocking. Another example that I can tell you, let me see what page is page 15. Look at here. We have our objective is to see the difference between the tire brands. So we have 4 different tire brands, and let's say at the beginning we won't consider this blocking. We would have something like this. We have the tire brand, A, B, C, D, and then we are gonna read data for it. Like we have, let's say, 4 tires of A, 4 tires of B and C and D, and then randomly we are gonna install it in different cars. We don't care about the cars when we don't consider the blocking, and we are gonna record the data. So what happened is that, for example, this 17, 14, 13, I can change their order. It doesn't matter, right? So it's just that I'm gonna record these data. So what happens is that, but the way that a driver would drive a car, like the time that they're going to brake, so you can see there is a trend in that, right? So what do we need to do is that we would need to say that, okay, so let's have like this set of data, like this set of the tires for this specific car. And then like this set of data for this specific car, this set of data for this, like we're gonna name it like car number 1, 2, 3, 4. And then we would have like tire A, B, C, D on them. So it's got install on them. And then the driver is gonna drive the car. So it's gonna drive like let's say tire A, B, C, D, all of them at the same time. And then we're gonna record the data. What happens is that the benefit here is that when I consider the source of the variation of the block as when we consider this source of variation and like with different cars, I'm removing that one as from the error. And because if you don't do that, it's going to be, you remember on our table, we had the source of variation and there were like regression model, or if we have like anything between treatment, within treatment, those ones, right? But generally it was like this. You had your regression model. Right now, like from now on, because we want to go to the details of it, when we say regression model, each of those factors that we had, like x1, x2, x3, those ones are the source of variation. We are going to deal with them like separately. And then we had error. So if you don't consider the blocking, what's going to happen is that the blocking as a source of variation is going to go inside the stomach of the error. Your error is going to be huge, right? And then you later when you want to do the analysis, ANOVA analysis, and you want to find out your F observed for each of those source of variation like factors, you are going to divide it by the amount of the mean square of the block as well, because mean square of the block is going to be inside the error. Because of that, we separated that the rest of the errors, they can show themselves better. So we could see the effect of the rest of the errors better. That's one of the huge benefits that they're going to get. In my opinion, that's the best benefit that we can get in the from the blocking. Because if you don't consider the blocking, the effect of the blocking as a source of the variation, so that blocking is going to go to the inside the error is going to be involved in the error part. And your error is going to be huge. But in reality, you can control the blocking, right? Then I say that, okay, so this is it's not uncontrollable. For the error, we prefer the ones that we can't control it, we just can measure it, or directly or indirectly, we would have it in error. But blocking, we can control it. Like I can say that, okay, so these are I'm going to have 4 cars. Each car has like the 4 sets, like it's going to have 4 tires in it. So this is the way that I'm going to control this one. If you have question about it, please let me know. It's really good. Like if we get the concept here, it's going to be very helpful for us later when you're working like in the labs and you want to, most of the time we have blocking, and unfortunately, most of the time we don't consider it. But if you consider blocking, you're going to make your error smaller. You're going to make your amount of the error, like source of the variation. And you're going to measure the real error, because blocking, you can control it, and you would have a source of variation as block. I'm going to, in this example, we'll see the how we deal with it. Okay, so look at here. I have the cars 1, 2, 3, 4. I tried to write it down on the board. So when I go and work on the board, we're gonna make the screen larger, and you would see that. I have the these numbers, and then I have the tire brands. Like we said that we have 4 different tire brands that we want to compare them together, and then we want to treat the data, analyze the data. So I wrote it down on the board. Look at here. I wrote down the cars here, and then we have the brands like this. These are the data that we read for each of those. And then I'm gonna write down the average, like the sum of them, that later when we want to do the calculation, it's gonna be easier for us. So for each of these, like 17 plus 14 plus 13 plus 13, so I will add it here, and it's then 57. And then this one is 49. This one is 43. And the next one is 44. So these numbers are that when I add, like this is the tire brand, right? So I will add what's going to happen for like all the data that I have in under the tire brand A, for example. And then I would have it for B, C, D. Also, we would have for each of these blocks, I can add the observations that I have. So here, when we add them, it's going to be 56, 51, and then 47, 39. 47, 39. Okay. And then we would have a grand total. Like you can add these or these. It's going to give you the same, like adding all of these observations. Yes, it's 193. So whenever we say grand total, while we are working with the single factor and multi-factor experiments, whether we have blocking or not, because we can have blocking in the multi-factor as well, right? So we can have blocking everywhere when we are dealing with data. So when we say grand total, it means that the whole data points. Now, let's see what are we looking for. The next page is talking about the treatment, like sum of a square, block sum of a square, and the total corrected sum of a square. So the reason that we need to find out these sum of squares is that we want to make the Anova table so the first column, let's review quickly. So the first column was sum of a square, and then we would have the degree of freedom, and then we would have mean square, which was that you would say sum of a square divided by the degree of freedom, and then we would have the last one, which is the F observed, which is the main output. Also from the Anova table, there are 2 main outputs. One is the F, the value of the F observed that we find out. For example, here we are going to find out the F observed of the sum of a square, right? So F observed that we get from the sum of the square of the treatment. Of F observed that we get the treatments are these like A, B, C, D. So it has 4 levels. Our treatment is tire brand, and the levels, we have 4 levels for it. So we can get the F observed of the treatment. We can find out the F observed of the block, which is the different types of the cars that we have. And then we can have the total, like error and total. So we're going to do that. So let's go to I'm going to show you the equation that we have. Let me bring it up. All right, this is my handwriting. I would suggest that you would make it by yourself. This is the one that I would use it, for example, when I want to do the calculations. I tried to write down for you that what's the symbols that they use in Montgomery book, a reference book. But total, when we say grand total, you can write it by GT, or in the Montgomery book, you will see that it's Y and then it has 2 dots. Grand average is like the Y 2 dots and then there's a bar on top of it. And then, so this is the main one. If you have a single factor experiment, so we have the total, we have the treatments, we don't without blocking, you could use this equation. And then we have, let me go to the, let's see. Look at here. Here I wrote down the experiment with single factor and block. So we have the blocking. It's page 3 of those of that formula sheet. So we want to find out the SS of the treatment, of the block, and the error and the total for our Anova table, and find out the degree of, and we would write down degree of freedom. So for degree of freedom, you just quickly, by looking at it, you will say, okay, so I have 4, the number of the levels. Here is 4 tires that I would have, so it's going to be 4 minus 1, degree of freedom would be 3, for example. You can deal with it like this, but I'm going to write down like I would go through that. Okay, so let's have these equations here, and let's see what do we have here. Here, this is the table that we would have. It's very similar to the number of the data points that we have here. So we have the blocks on the first column, and then let me see if I can make it a little bigger. Okay, here. And then I would have the treatment here. And here's just an example, like the k equal to 4, n equal to 3. It's just the example that we have. The first step is that we want to find out the sum of the square of the treatment. And the equation that we have for the sum of the square of the treatment is the 1 over n and sigma treatment total power 2. I'm going to write it down on the board. Minus, this one is the correction of the mean. So correction of the mean basically is like this. We said that y bar is the grand total, right? So whatever grand total that we have, so here is 193, right? If you square it and divide it by this capital N is the total number of the observation. So here, if you want to find out the total number of the observation, you can say that, okay, so I have 4 columns here and like 4 here, for example, in this specific example. So the total number of observations, we can find it from that. So let me just write it down. So I'm gonna, I think it's better if I write down on the board, right? For the correction of the mean. So correction of the mean, we use it for all of the sum of the squares when we want to find it. So because of that, I'm gonna write like y bar, like y double dots square divided by n. So here is the, I'm gonna write it down. Correction of the mean, and it's equal to the grand total, right? So here I have like 1 factor and 1 block, right? So I would have 2 dots. These dots, in fact, is like it's the sigma. It means the sigma of all of these, like sigma from A to D, or sigma from 1 to 4. These dots when they put it on the bottom like this. And then if I had like 3 different, like 2 factors, like multifactors, 2 factors and 1 block. So, or 3 factors, in that case, you would have like 3 dots, for example, here. So we're going to talk about it later. And let's say y double dots here and then over 2 divided by the n. N is the total number of the observation. In this example, you have a small n equal to 4, and like you would have the, we can say 4 here and 4 here. So 4 times 4 is going to be 16. What we are going to do is that we would write down like whatever grand total it is, and then we would power 2 divided by the 18, 193. Let me just see. I feel that I did a mistake. Yes, it's 193. I didn't do it. So it's going to be 193 power 2 divided by 4 by 4, like 16. It's the total number of observations that you would have. So we find out the value of this, and the value of it is 2328 point something. Okay, so this is the correction of the mean. I would suggest that you would calculate it like this, or you can just, as you see in the equation that we have, you can simply write down this equation when you want to find out the sum of the square of the treatment, and you can put the correction of the mean here. It's the same. So I will write down here, we are looking for the sum of the square of the treatment, which is the same as the sum of the square of the tire brand here, right? And then the equation that I have is 1 over n at sigma, let's say I equal to 1 to k. And then I would have the treatment total. I'm just writing down the equation that we have over there. Treatment total power 2 minus correction of the mean. Minus correction of the mean. Okay, so let's see how we deal with it here. When we say treatment total square, it's like that. Look at here. These are my treatments, right? So whatever you have for treatment A, it's like that. You would say this 57. It's going to be this number power 2. So here I would have 1 over n is 4, right? And then, so for like, I have like this n is 4, right? And then the k, the level of the treatments that I have is 4 as well. So it means that I would have from 1 to 4, I would have it 4 times. Okay, the first treatment is the treatment total, like at each level, what's going to be your treatment total? So I would have it like, for example, here A, the treatment total is 57 over 2 plus 49 square, 43 square, 44 square, right? And then after we found this minus the correction of the mean, 2328.06. When we do this, we do the calculation, and here we found out like it's 30.7. This is how we find out the sum of the square of the treatments, or the sum of the square of the like tire brands that we have. And the brands are this one. So I'm going to write it down here, the sum of the square of the treatment, because I want to erase it and use the word. We found it 30.7. So the next one is that we want to find out the sum of the square of block. When we look at the equation, look at here, sum of the square of block is 1 over k, right? And then, so k is the number of the levels that you would have in each of these blocks. And then block total square, what did I write here? Here as well, each row. Minus the correction of mean. So it's very similar to this one. The only thing is that here we have like sum of the square of treatment. Look what I'm going to write down here. It's interesting because the logic is exactly the same. So like when we work with Anova, the logic behind the Anova is exactly the same. It's exactly the same thing that you would have like, whether you have in the basic level of the stats that we had in the second year, it's exactly the same that you're going to have in the intermediate level, that is this course, and then the advanced one, which is the surface modeling course. The logic is the same. So if we learn this logic together like once, then we're done. So now look at here. We are looking for the sum of the square of brand, and like block, not brand, sorry. A block, which is the car. So it's going to be sum of the square for the cars. And then I would have 1 over, here was n, because n was showing us that how many number I would have in one column. But here is going to be 1 over k, because k is the number of the, like from here you can say k is equal to 4. And from here you can say n is equal to 4. Okay, so 1 over k. And then you would have block total, like each block, what's going to be the total of it? The block total square minus correction of the mean of it, like for the whole. So you can do that by yourself. While I'm doing that, it's going to be 1 over 4. And then for block total, I have these values, right? So it's 56 over 2 plus 51 over 2 plus 47 square plus 39 square minus the value of the correction of the mean. I have it over there, 23, 28, 06. And then total of it is, I have it somewhere written, the final answers, 38.7. So here I'm going to write it down, SS of the block. It's going to be equal to 38.7. So far, I have the treatment sum of a square and the block sum of a square, right? The next one is the SS of total that we need to find it. We need to erase this. And so for sum of a square of the total, we would say, you can see that here is sigma, like y, like all the observations that we have, a square, and minus the correction of mean. So what happens is that I would have, if I want to write down the total sum of a square, I would write it down here like this. Sum of a square of the total is going to be equal to sigma. I would say sigma because I have like only, we have it for the n, right? And we have it for k. So I can write down, let's say I can have symbol for it. I could say that, let's say, one is I equal to 1 to, let's say, n. The other one is t equal to 1 to k. So it's up to you. It doesn't matter that I can write down j as well. And then in the equation, I have y of the ti, let's say, a square minus correction of the mean. The logic is very interesting. It's exactly the same. So what's going to happen is that I would have each of these observations, whatever you have, you're going to square it. So I would write down 17 square plus, I'm going to write 17, 14, is by n, so let's go this way. 17, 14, 13, 13. 14, 13. It doesn't matter. It's like that. We're going to add all of them. 14 square. And then we would do that until we reach this one. Like 11 square and a square minus the value of the correction of the mean, which was 23.28. 06. So we do the calculation and just bring it and it's going to be 80.9. So here I'm going to add it SS total. It's equal to 80.9. So we have the sum square of treatment, sum square of block, sum square of total. Now we can go and do the Anova table. However, I think that's a good idea if at this point we find out the degree of freedom as well. It's going to be easier. We're just going to write it down next to it. So you see that how I make it. So I have like a, on the right, I have something like this. I would have all of my data points. It's going to be very helpful if you do that, because if you see that, for example, you see the sum of the square of total is much smaller than these two numbers, for example. You can quickly fix it before going to the next step. So sum of the square of total should be the largest one, right? So if I find this one is smaller than one of these, it means that, okay, there was something right, it's some mistake. So now, let's go back to our like Anova table here. Oh, we wanted to write down degree of freedom, I forgot it. So I'm gonna write down the degree of freedom. The degree of freedom of treatment, I will write down here like this. Do something even better. Let me just see. Erase this first and then write down here. So degree of freedom of treatment is going to be whatever number that you have for the treatment. We had K level, right? So it's going to be K minus 1 equal to 3. 4 minus 1 equal to 3. And then I have the degree of freedom for the block. So I write down here, degree of freedom of block. It's going to be N minus 1. It's going to be 3 as well. And then for the total degree of freedom, you would say that degree of freedom of total. One thing that you can do is that you can say, okay, whatever number of observations that you have, here is 16 minus 1. So it's going to be, you can write it down like that, 16 minus 1. It's going to be 15. Or you can say that, okay, so let's say how many number of the blocks and how many number of the levels, like for the factors that I have. And then we would say that, okay, so it's like 4 times 4. So it's going to be 16, right? Or you can say that, okay, total number of observations that you have minus 1. So we have the degree of freedoms as well. And the next one is the Anova table. So the main focus, we did all of this, that you would go and find out the Anova table. So for the Anova table, we have a source of variation. And you can see that we have the treatments. I'll make it a little bigger. So we'd say between treatments or within treatments, which is like the block. So I would write down treatment, block, error, total. That's how we would write it down. And then we have the sum of the squares and the degree of freedoms. So here, I would write it down like this. ANOVA. Here is the source of variation. So I would have it for treatment. Here, the treatments are the brand, tire brands, tire brand. And then I would have it for the block. And here the blocks are the car. And I would have it like error, and I would have the total. Okay? And we said that the first column is sum of a square. Okay? The next one is the degree of freedom, mean square, and F. Okay, so for sum of a square, I wrote it, we have it here, right? So it's 30.7. For the treatment, for the block is 38.7. Oh, I have to write down. So for block here is 38.7. And then I have for the total 80.9. So we can find the error one. So for error, what are you going to say? We will say is 80.9 minus 30.7 minus 38.7, which is equal to 11.6. Okay. And then degree of freedom, we said that this one is 3. And for the treatment, degree of freedom of block is 3 as well. Degree of freedom of total was 15. So I'm gonna, I'm going to erase this, but you know that how I wrote it down, right? So even you can pause it, pause the video, and write down the 11.6 here that I could have enough space for degree of freedom. So for degree of freedom, I would say 15 minus 3 minus 3, right? 3 minus 3 minus 3 minus 6 is going to be 9. I would have it 9. The next step is the mean square. So when we look at let's look at this equation. So we have the sum of the squares, and here is written that this total minus SS minus S block, and then we have the degree of freedom. We write down the degree of freedom for it. So you can go through this equation. I would suggest that you would go conceptually, because when we go with the multi-factor experiment, you will see that the concept is that, okay, degree of freedom of total is going to be whatever total observation that you have minus 1. You can say here k, a small k times 1, because we have k here and n here, minus 1. And then we have the mean square. And for the error, you can say k minus 1 times n minus 1. Or you can, like, other degree of freedom that you have for this one and this one, you can multiply it. Or you can simply say, okay, so I have 15 here, minus 3 minus 3. This is a total degree of freedom, right? So for MS, we said that whatever you have for the sum of a square divided by this, it's going to give you this. Whatever you have for the sum of a square divided by this is going to give you this. So 30.7 divided by 3, which is going to be 10 point something. You see the if I know. It's 10.23, and we do the same thing, 38.7 divided by 3, so it's going to be 12.9. 11.6 divided by 9 is going to be 1.3. This 1.3, which is the MSE, is the same as the sigma 2 square. Like, it's an estimate for the variance of the whole process. The next one is F observed. So we make the Anova table to find out the F observed, right? And when we are looking at the equation here, look at here. This part is very important. When we want to find out the F observed, whatever you are, for example, you want to find out the F observed of the, let's say, treatment. So you would find out the MS of the treatment, and you would divide it by the MS of the error. So here, this one, the mean square of error, right? So whatever you find here, you would divide it by this number. I will write down 10.23 under this, like I would fit it in this column. So what's going to happen for F observed of the treatment? I would say 10.23 divided by 1.3. For an F observed of the block, I would say 12.9 divided by 1.3. So here, when we do this, the final answer is going to be 7.8. And the final answer of this one is going to be 9.9. What I can do is that, because we don't have enough space, I can write down 7.8, and this one is 9.9. Okay, so we found that the F observed, and then we would need to go to the table with the F critical. So for F critical, let me have this. F critical. What happens is that we need to write down the degree of freedom of the numerator, degree of freedom of the denominator, right? And then the alpha that we have. So here, just make this one a little smaller. Okay. So here, what happens is that the degree of the, let's say, because we have the degree of freedom of 3 and 3, so the F critical that I will read from the table is going to work for both of them. So I would have like 3, and then denominator. Like, what's the denominator when you want to find out 7, 8? It's like this error, right? So degree of freedom is 9, and then I would say 0.05 because we didn't have anything like, right? Then we can go to the table. Let me find my book. Okay, we go to the F table. And from F table, for the 0.05, so here I have the, I'll show it on the screen. You can see the board, right? Yeah, that's good. I checked out at the beginning of our session. So this is the F table that I have, and this is the book, our reference book. At the end of any Montgomery book or any stats book, we would have these tables. So with this F table, I have here is written degree of freedom of denominator and degree of freedom of the numerator. So for denominator, we said that is 9. For numerator, it was 3. So look at here, maybe like this. So I would go here and I would go to 3, right? And when I reach the 1, 2, 3, 1, 2, 3, I will see reverse side. I'll go down. So this one represents the numerator. And for 9, then I would read the F from it. So you can see that here when I look at it, it's 3 and 9. So it's this number, 3.89. So we would read the value from the table, 3.89. Now we can compare it, like compare the F observed and the F observed of each of these one, like the treatment and block with it. We would say that, okay, so let's see what's going to be the, this is the F observed of the treatment. Just so the F observed of the treatment is 7.8, so it's greater than F critical. And also F observed of the block is greater than F critical as well. So what does it mean when we say that? It means that so when we find out the F observed of the treatment is greater than F critical, it means that, okay, so we need to consider this treatment. It has significant effect. So when F observed of the block is greater than F critical, it means that, okay, we need to consider the F of the, like, the effect of the block. So I'm going to go back to the lectures. Here is the Anova table that we have. I'm going to sit a little while I'm talking about it. So look at here. We found that the F observed and F critical is like that. The F observed, we compared that, and for both of them, they're greater than F critical that we would have. So we would say, okay, therefore, brands like the treatments do not show the same amount of fear. So it means that they're significant. So they have like this one is different than this one, than this one, than this one. So we need to consider it. It's we need to consider the effect of the brand. So after this, if you want to compare 2 by 2, you would go to the T comparison or LSD comparison or LSD Bemperoni comparison. But it's like that. Up for the first step, we said that we are going to do find out the F table to see that if there is any difference between these brands. Are these brands, like, are these treatments like different levels that we have for our factor? Is it effective or not? And also the thread loss for the cars and the blocks, they are not the same either. So it's like that the effect of the cars, you can see that we need to consider the block.